Okay, so our internal calculation bore some fruit. We honed in on the place where we knew information, and from that we were able to come up with the velocity of the system of the particle at the entrance and exit point of the window. And so that tells us something new. You know, this thing's getting complicated. And so I have a large stack of blank scratch paper, and so there's no necessary, you have to clutter the same figure again. So I'm going to draw a new schematic down here. I know that this is 1.4 meters. It passes through here in 1.4 seconds or 0.15 seconds. And now the balloon starts from where it exited the window, and it comes to some height where it comes to rest. And that's one of the things I'm looking for here, which is how high above your window did it go. And since I think I can solve for that now, I'm going to work on that problem. So let's establish a coordinate system. And in this case, I'm going to put my 0 of my coordinate system here at the initial point, and I'm going to call up my positive x-axis. So you see, you don't have for each stage of the problem, if your problem has multiple stages, you have the freedom to change your coordinate system, which I'm going to do in this case. So now let's figure out what we know for this stage. My initial time, which I also get to choose, I'll choose to be 0. My final time is something I don't know. My initial position, given this coordinate system, is 0. My final position, that is where I'm saying where it comes to rest at the highest point of the trajectory. That is unknown. My initial velocity, I do know. It's my final velocity from my previous internal calculation, because it told me that velocity is the velocity where it exits the window. And this is pretty important. A lot of students, even if they figured out to start, let's go back up here, to start looking at these 2 points in time. In fact, many students just might do that, because that's sort of the only, if they didn't think about it too much and didn't visualize very well, they say, well, here's 2 points in time, I'll just do that. And oh, this gives me something to calculate, and so they calculate it. And so at this point, they say to themselves, okay, I've now found v sub I, and that's 10, and v sub x, which is 8.6. What do I do with v sub I and v sub f? And then they get stuck. And the key here is not to think about these as v sub I and v sub f. That's just a notation. These relate to real velocities from the trajectory. How physically do they relate to the problem you're trying to solve? This v sub I is the velocity when it enters the window. This v sub f is the velocity when it exits the window. And so now when I go to the next stage, there is no confusion. This is not a v sub I. It is the velocity when it exits the window, which is this number. So as long as you always relate what you're calculating to the physical problem with a very good picture, a very good visualization of what is happening, you use that context so you don't confuse one velocity from another, and you use that context to be able to show you where to go next. Okay, so now in this problem, the final velocity, well, that's my initial and final. That's the point where it reaches the highest point of its trajectory. Well, at the highest point of a trajectory, the velocity is 0. So the final velocity is that. Okay, and so now I have, let's see, I know my velocities, and I know the acceleration, which is still negative g. And it looks like I have plenty of information to solve now. I'll go back to my handy relationships, and it looks like right here I know initial and final velocity, I know my acceleration. I can come up with the displacement. So I'm going to use that to solve for how high it goes. So the final velocity is 0. The initial velocity so that's the initial velocity squared, is equal to, plus twice the acceleration, which is negative g, times the displacement, which is xf minus x initial. Okay, initial is 0, so that goes away. So I bring this over to the other side, it's negative, and I can solve for x sub f. And x sub f is equal to then v initial, x squared, divided by 2g. When I bring this to the other side, it gets a negative sign. This negative sign turns it positive, so I have a positive vix squared over 2g. At this point, I can plug in my values for 8.58 and put it in my calculator, and I'll get something like 15.087. And so this now gives me my answer to part B of this problem, the final position, which I'll call 15.1 meters. So note that I didn't let the problem, the order of the questions, bug me. I ended up solving for part B first, and there's nothing wrong with that. I went to the direction that the problem led me. My final answer, I was going to have, I brought down to a reasonable number of significant figures. I kept further for my internal calculation. My answer has about 3. My answer makes sure I have my units. A lot of times, I don't include units on a lot of my internal calculations. As long as I know that everything starts in SI units, I don't, it's a little cumbersome to keep them through all the way to the calculation, but you always have to remember at the end to make sure that you have the right units for your problem. Okay, so now we're to the final part, which is how long does it take to go all the way around before the projectile comes back to the window. So now it leaves here, it goes up and comes back, all in one dimension, but eventually it comes here. Okay. Well, let's do 2 points in time again. I might erase this. I'm going to keep the same coordinate system, my 0 here, positive x, that makes sense. But in this case, I'm going to use as my initial time the time that it leaves, and the final time to be the time that it reappears. All right, so what does that give me? Okay, I'll move down a little bit. I might resketch my window. So here I have, comes up, comes back down, my initial, final, positive, x up, here's my 0 at the top of the window. Okay, so now what do I know and what do I want to find out? Okay, so my initial time, I'm just going to call that 0. I have the freedom to do that. My final time then is what I'm trying to find. My initial position, which is given this coordinate system, is equal to 0. My final position, also given this coordinate system, is also 0. So that's kind of interesting. Okay, what's my initial velocity? Well, it's going up, so it's positive, and it's the velocity when it exits the window, which is 8.598 meters per second, and it's positive. And we have the final velocity, that's when it comes back down. Now, I happen to know, and maybe I've already proven this to myself, that this sort of trajectory is symmetric about the top, that the magnitude of the velocity when it crosses the window, the same position, is in fact the same magnitude of the velocity that it started, just going in the opposite direction. But maybe I don't know that. Maybe I'll just leave that blank for now. The thing is, I have plenty with these. With these expressions, I already have plenty to solve for the time, because if I go up to my expressions right here, I know my initial velocity, my initial final position and my acceleration so I can solve for the time. Okay, so let's go ahead and do that. If the final position is 0, is equal to the initial position, which is 0, plus the initial velocity times time, plus 1/2 acceleration, which is negative g times time squared. So the zeros go away, and this now has two solutions. The first solution I identify right away is t is equal to 0. If t is equal to 0, this equation is satisfactory. But the answer is not satisfactory. Again, I know from logic that it can't instantaneously travel the entire trajectory. So while this is a proper mathematical solution, it is not a proper physics solution to the problem. Okay, but I can do some algebra here. Since this is equal to 0, and I have factors of t in both expressions, I can divide both sides by t, and I can get rid of a factor. So now I have 0 is equal to v x sub I minus g over 2 t. So now I can solve t sub f, right? This is my final time. So my final time then is equal to 2 v times my initial velocity over g. When I subtracted this on the other side, it became positive, and then divide both sides by g over 2, and I get this expression for my final time. Now I can go ahead and plug in numbers for this, and g is 9.8. Oh, I didn't even notice that. My acceleration, negative g in the x direction. But put in those values, and I get for my time is equal to 1.75 seconds. Okay. So this is the type of problem where when you first read it, and this is part A, it's not exactly obvious how to solve it. And so this is where you need a strategy that will take you somewhere, that will get you further into the problem until you get to the point where you can see how to solve it, which is why the brainstorming part of problem solving is so important. And so we used the brainstorming, started with what we knew, to be able to extract more information. And once we had more information, then we started to accumulate a direction of how we could get to the final answer. And it also illustrates why it's so important to have clear visualization of what's going on, to be able to extract physical context from the problem, to be able to understand what the terms mean, and good pictures and schematics and diagrams. And the other part is, if you're doing a multi-stage problem, you have the freedom to choose your zeros of your coordinate system and your directions for each stage of the problem, as long as you understand the physical meaning of the results and can relate the physical meaning to the different stages. For example, where here the final velocity in this stage was the initial velocity of this stage, because they both related to the exact physical entity, the velocity of the particle leaving the window frame. And so those are the types of techniques and tactics that you want to become familiar with to become better at solving these types of problems.